After studying this module, you shall be able to know about various models for the anomalous magnetic moments, learn how magnetically non-equivalent sites in the unit cell gives rise to anomalous magnetic moments, identify solute-solvent interactions and solute-solute interactions which are responsible for anomalous magnetic moments. Evaluate the extent of solute-solute interactions in nickel and cobalt complexes.
Prerequisite. Before going into details of this module, you should be aware of anomalous magnetic moment. Anomalous magnetic moment is the magnetic moment for a metal ion in a discrete molecular species having a value which falls outside the range of values predicted from considerations of the spin and orbital angular momentum in ligand fields of given strength and symmetry. The discrete molecular species means that there is no secondary magnetic interaction between the neighboring molecules. In other words, for these systems, there is not any ferromagnetic or antiferromagnetic interactions. It explains these systems are magnetically dilute. A variety of models have been proposed to account for the anomalous magnetic moment of different metal complexes. These may be discussed under the categories. First, equilibrium between two spin states. Second, magnetically non-equivalent sites in the unit cell. Third, solute-solvent interaction. Fourth, solute-solute interaction. Fifth, configurational equilibrium. In the previous module, we discussed about equilibrium between two spin states. In this module, we'll start our discussion from magnetically non-equivalent sites in the unit cell, and then we'll discuss solute-solvent interaction, solute-solute interaction, and configurational equilibrium. Introduction. A variety of models have been proposed to account for the anomalous magnetic moments of different metal complexes. These may be discussed under the categories: equilibrium between two spin states, magnetically non-equivalent sites in the unit cell, solute-solvent interaction, solute-solute interaction, configurational equilibrium. Magnetically non-equivalent sites in the unit cell. The coexistence of metal ions with two different stereochemistries or geometries within the unit cell can also give rise to anomalous magnetic moments of the metal complexes. There can be two situations responsible for magnetically non-equivalent sites in the unit cell. First is the metal ions have the same coordination number and the same set of attached ligand but having different geometries. Second, the metal ions have two different coordination numbers, hence different geometries within the unit cell. Magnetically non-equivalent sites in the unit cell are well known only for nickel 2 plus complexes. The example for the first situation is the green nickel 2 plus complex, that is dibromo bis benzyl diphenyl phosphine nickel 2. The complex has an anomalous magnetic moment of 2.7 Bohr magneton. The X-ray crystallographic studies of this complex suggest that there are 3 4 coordinate nickel atoms in the unit cell. One unit is square planar and two units are tetrahedral. Remembering the additivity of square of the magnetic moment and taking into account the mole fractions of the two form. If gamma sp and gamma td are the mole fractions of square planar and tetrahedral nickel species respectively, moreover, mu sp and mu td are the magnetic moment of the square planar and tetrahedral nickel species respectively, then we have mu square is equals to gamma sp mu sp square plus gamma td mu td square. Now putting the mole fraction values mu sp and anomalous magnetic moment value in the equation, we find out that mu td is equals to 3.3 Bohr magneton. Since considering only two of the nickel atoms being high spin, the moment of the tetrahedral nickel atoms come out to be 3.3 Bohr magneton, which is in good agreement with the values generally observed for nickel in pseudo tetrahedral environments. The spin isomers, as just discussed, differ only in bond angles as termed as interallogon. An example of the second type of isomerism has been observed in a yellow form of the Lifschitz compound, which is bis-mesostilbene diamine nickel 2 dichloroacetate 2 by 3 ethanol 4 by 3 water. The complex has an anomalous magnetic moment of 2.58 Bohr magneton. The X-ray crystallographic studies of the complex suggest that the unit cell contains both 6 coordinate means pseudo octahedral and 4 coordinate means square planar nickel 2 plus complexes in the ratio 2 is to 1. The square planar nickel 2 plus complex has two bidentate stilbene diamine coordinated to nickel 2 plus, and the distorted octahedral complex has two stilbene diamine along with two water molecules at axial positions. Remembering the additivity of square of the magnetic moment and taking into account the mole fractions of the two form, if mu sp and mu oh are the mole fractions of square planar and octahedral nickel species respectively, moreover mu sp and mu oh are the magnetic moment of the square planar and octahedral nickel species respectively, then we have mu square is equals to gamma sp mu sp square plus gamma oh mu oh square. Now putting the values of mole fractions mu sp and anomalous magnetic moment mu, we get mu oh is equals to 3.17 for each paramagnetic ion, a value that is completely consistent with high spin 6 coordinate nickel 2 plus complexes. The color of Lifschitz compound varies from yellow to blue depending on the nature of anion, the coordinating solvent, and diamine used. Quinoxylon complexes of nickel 2 halides provide another interesting examples of second type of isomerism. The quinoxylon complex of nickel iodide is diamagnetic. However, the chloride and bromide are paramagnetic tetragonal polymers involving bridging halides and quinoxylon complex groups. The quinoxylon complex with nickel bromide exists in two forms. The spectral studies show that the brown isomer has an anomalous magnetic moment, that is 3.51 Bohr magnetons. The brown isomer contains two stereochemical components within the unit cell. In this case, alternating tetrahedral and tetragonally distorted octahedral are suggested coexisting in a polymeric structure involving bridging bromides. Since the nickel atoms are high spin in both environments, a resultant moment in excess of 2.83 Bohr magneton is to be expected. Solute solvent interactions. An anomalous magnetic moment may also arise when a particular species interacts with a coordinating solvent. Thus, many nickel 2 plus complexes, which are diamagnetic in solid state, become paramagnetic when dissolved without gross decomposition in a variety of solvents. In many cases, the paramagnetism corresponds to a moment per nickel atom of less than 2.9 Bohr magneton. Similarly, certain cobalt 2 plus complexes appear to undergo changes from S is equals to half to S is equals to 3 by 2 upon dissolution. Such changes may come as a result of several possible types of interaction. The character of the solvent is the key factor in determining the type of interaction that occurs. Generally, most of polar solvents have a strong ligating atom such as nitrogen or oxygen. These strong ligating atoms can act as moderate d orbital perturbation factor, results in the change of coordination number and spin state of a particular species. Such cases are well known for nickel 2 plus complexes and can be extended to cobalt 2 plus and even Fe 2 plus complexes. Several bis salicylyl diamine nickel 2 complexes are diamagnetic in the solid state and fully paramagnetic in pyridine solution, a phenomena which they attributed to the formation of 6 coordinate pyridine adducts. In this case, it was assumed that the origin of paramagnetism is due to interaction of solvent with the square planar complex and corresponds to the equilibrium solvent plus square planar gives pseudo octahedral paramagnetic complex. The nickel 2 plus complex of a macrocyclic ligand shown on the screen shows similar behavior in water, pyridine and acetonitrile. The equilibrium is observed for the complex in water. That is, diamagnetic species is changing into paramagnetic species on addition of water. The spectroscopic and magnetic studies reveal that the thermodynamic parameters delta H and delta S values are concentration dependent because of changes in solvent activity. Solvent activity may be particularly important in determining the position of the equilibrium and hence influences the magnetic moments of such systems in solution. The addition of extraneous salts to aqueous solution reduces the activity of the solvent, water, thus influences the relative amounts of spin-free and spin-paired complexes. For example, nickel diab 2 exists as nickel diab 2 H2O2 in aqueous solution. And in the visible spectrum of the complex in water, a new band is observed on the addition of extraneous salt with a decrease in intensity of the band already present. This new band could be assigned to a transition of square planar nickel produced by loss of two water molecules from the complex nickel ion. This loss of water is apparently a result of the reduced activity of the solvent water. The similar equilibrium is also shown by some cobalt 2 plus complexes. For example, cobalt L2X2 where L is the pyridine, substituted pyridine or isoquinoline. In this case, the equilibrium proceeds from a tetrahedral form to octahedral structure. This equilibrium involves two paramagnetic species with only slightly different magnetic moments. However, careful measurements should indicate a change in moment with an increase in the amount of octahedral complex. The anomalous movements are also observed for solution of nickel and cobalt complexes in so-called inert solvents such as chloroform, carbon tetrachloride, carbon disulfide, benzene, etc., and some coordinating solvents which do not interact with the complex. For the nickel 2 plus complexes in inert solvent, diamagnetic, planar, paramagnetic tetrahedral or octahedral rearrangement is possible for the anomalous movements rather than solvation. Example given: for the solution of bisformyl camphor ethylene diamine nickel 2 complex in methyl benzenes, there is no direct correlation between the paramagnetism and base strength of the solvent. This indicates that the formation of tetrahedral species rather than solvation is responsible for the paramagnetism. It can be concluded that interaction with solvent is not a necessary condition for the development of paramagnetism. It appears the two models consistent with most of the experimental evidence are solute-solvent interaction and second, planar tetrahedral equilibrium. Similar behavior in both categories has been found for cobalt 2 plus complexes. Solute-solute interactions. The solute-solute interaction means an association of two or more molecules of a complex leading to an increase in coordination number of metal ion. This interaction changes the spin state of the metal ion. Nickel complexes, for example, the green diamagnetic complex bis N-methyl salicylyl diamine nickel 2 turns into a buff-colored paramagnetic complex of the same composition when heated above 180 degree. This buff-colored complex has a magnetic moment of 3.2 Bohr magneton at room temperature, corresponding to the presence of two unpaired spins per nickel atom, and is insoluble in a large variety of solvents in marked contrast to the soluble green diamagnetic isomer. The magnetic moment is nearly independent of temperature in the range 115 to 350 Kelvin. The buff-colored paramagnetic complex is polymeric and having octahedral geometry. The sixth coordination is attained by stacking of the planar units in such a manner that the oxygen atoms of adjacent molecules interact axially with the metal ion as shown here. Moreover, the same complex shows an anomalous magnetic moment in range from 1.9 to 2.3 Bohr magneton in solution, depending on the nature of non-coordinating solvent. The moments of higher members of the N-alkyl series means ethyl to N-pentyl are lower. The dipole moment of the complex in benzene or dioxane is zero, thus ruling out the planar tetrahedral conformational equilibrium. If the concentration of the complex in any such solvent is increased, the molecular weight and magnetic moment also increases. This indicates the presence of solute-solute interaction, solute association in solution of the higher N N-alkyl substituted analogues is apparently less. This being mainly monomeric and diamagnetic at ordinary temperatures, if steric barrier is introduced via substitution on the benzene ring, then there is decrease in solute-solute interaction. For example, the presence of a substituent in the 3 position of the aromatic ring eliminates the paramagnetism in N-methyl series, whereas substituents in the 5 position are less effective. because the substituent in the 3 position does not allow the phenolic oxygen to get attached axially to the second nickel 2, thus preventing the change of spin state. The solute-solute interaction is the pressure dependent. Solid complexes subjected to high pressures show a small increase in susceptibility. But this does not result in isolation of a solid exhibiting permanent polymerization. N-aryl substituted salicylyl diamine complexes show different behavior. The controlling factor of magnetism in these complexes is the nature and position of substituents X and Y in the aryl ring. The complexes containing Y in the 2 position are diamagnetic both in the solid and in solution. They are also monomeric in solution. The diamagnetism is retained even at higher temperatures. This suggests that the presence of Y substituents in the 2n aryl position or of X substituents in the 3 position of salicyl diamine ring demand that N-aryl ring to be rotated out of the plane of the chelate rings, thereby preventing the lateral association, and there is no solute-solute interaction. One exception is the complex in which Y is equals to toluyl at position 2 and X is equal to isopropyl at position 3. This complex is weakly paramagnetic. All the complexes with no any substituent at the 2 and 3 positions of N-aryl and salicylyl diamine rings respectively show solution paramagnetism to a greater or lesser degree. There is a satisfactory correlation between solution movements and degree of association for most of these systems. There are few exceptions. For example, the N-phenyl and N-p-fluorophenyl complexes show solution paramagnetism greater than can be accounted for solely on the assumption of solute association. The magnetic and spectral measurements of these complexes in xylene or bibenzyl solution suggest the presence of tetrahedral species along with the associated 6 coordinate molecules. Therefore, 3 forms of N-aryl complexes can coexist in solution that are associated paramagnetic form, planar diamagnetic form, tetrahedral paramagnetic form. At room temperature, the proportion of molecules in the associated form is greater than 80%. With an increase in temperature, the percentage of tetrahedral form increases significantly. The same shift in equilibrium should be achieved isothermally by dilution. Cobalt complexes. The solute-solute interaction is also observed in cobalt 2 plus complexes. The complex bis-N-methyl salicylyl diaminato cobalt 2 achieves 5 coordination by association in the solid state. As a result, this complex has a moment of 4.62 Bohr magneton. However, the solution of the complex in benzene is monomeric and tetrahedral at low concentrations. No moment is reported for the complex in solution. The complex bis-acetyl acetonato cobalt 2 is high spin square planar complex with mu effective is equals to 4.8 to 4.9 Bohr magneton. in the solid state and in solution. The spectral study suggests that this compound is tetrahedral in the monomeric state. In addition, it shows the concentration dependent association in non coordinating solvents. Consequently, this complex can be isolated in several forms: bis acetyl acetonate cobalt 2.2H2O, bis acetyl acetonate aqua cobalt 2, bis or tris bis acetyl acetonate cobalt 2 dot H2O, tetrakis bis acetyl acetonate cobalt 2. The central portion of the tetrameric species bis acetyl acetonate aqua cobalt 2 is shown here with bridge bonds on the two faces occupied by water molecules. So, regardless of the stoichiometry, the complex achieves 6 coordination and high spin character. It is possible for association to lead to a low spin form for cobalt 2 plus complexes. The magnetic moment and electronic spectra of the complex depends on temperature and concentration of the complex in dichloromethane and dichloroethane solutions. It is due to the equilibrium monomeric high spin tetrahedral is changing into dimeric low spin 5 coordinate. The 5 coordinate dimer using bridging thiocyanates, the reaction of the complex with excess of triethylphosphine causes a decrease in observed movement from 3.4 to 2.05 Bohr magnetons. This is due to the formation of 5 coordinate complex shown on the screen.
In this module, we discussed that anomalous magnetic moments can be generated by the existence of metal ions with two different geometries within the unit cell. Some of nickel 2 plus complexes are examples of magnetically non-equivalent sites in the unit cell. In a complex, 4 coordinate nickel atoms in the unit cell can occur in square planar as well as tetrahedral geometries. This gives rise to anomalous magnetic moment of the complex. When a particular species interact with a coordinating solvent, this also gives rise to anomalous magnetic moment. Thus, many nickel 2 plus complexes which are diamagnetic in the solid state become paramagnetic when dissolved without gross decomposition in a variety of solvents. The solute-solute interaction means an association of two or more molecules of a complex leading to an increase in coordination number of metal ion. This interaction changes the spin state of metal ion.